in them all up. So looking at the green, because it's nice and big, we have the standard enthalpy change for a reaction is 2 moles times 33.8 kilojoules per mole minus 1 mole times 0. Why is oxygen 0? What does delta H0 sub F mean? It means how much energy does it take to make this from elements in the natural state? How much energy does it take to make oxygen from oxygen? None, right? That's why it's 0. So all elements in their natural states will be 0. And then minus 2 times 90.37 kilojoules per mole. The moles cancel, we add them up, and we get negative 113.1 kilojoules. Don't forget to put the units down there. I see one group didn't have units. Okay, any questions on using enthalpies to calculate enthalpy of reaction? Okay, on the next page is a really hard problem. This is a Hess's law problem with a twist because it involves enthalpies of formation. Now, for my morning class, I gave this to them as a take-home quiz because they had already done that other problem that I just assigned to you as a take-home quiz. They turned it in today. So would you like to have 2 take-home quizzes for Tuesday? I think so, because it's 2 good problems to practice as you're preparing for the test. You bring them in Thursday. I will be in the public meeting place to meet with you before class. And that Tuesday, what did I say? Thursday? Tuesday. Tuesday. The test, hopefully it's Tuesday. Hopefully we're going to finish this up. Or we're going to come in on Saturday. So this is also a take-home quiz.
Are they 10 points each?
Sure, 10 points each. Because we've already got 11 quizzes in, this will be 12 and 13. That gives you a chance to drop 3 low quizzes. And then after next week, I don't think we're going to have time to even think about quizzes. I think we're going to be done with quizzes as we do the last chapter. But we'll see how things work out. Okay, so you have 2 take-home quizzes due at the beginning of class on Tuesday for this section. All right, now let's talk about another way to calculate energy changes for reactions. Another way to look at the enthalpy changes of reactions is to deal with bond enthalpies or bond energies. Because we can think about starting with reactants, breaking any bonds in the reactants and making any bonds in the products. So we can do this as another way to calculate energy. But in order to do this, you have to know what kinds of bonds are breaking. So calculate the enthalpy for this reaction using bond energies. You need a table with bond energies, and this is in your book. It's on page 407, table 10.4. So remember, that's my page 407. It's the little one in your book. So when we look at this, the first thing we do is say, well, what kind of bonds do I have? So we start off, always balance the equation. It is balanced. Now we're going to draw Lewis structures so we can think about the bonds. So methane, CH4. We have 8 electrons. We make 4 single bonds. We have 2 molecules of oxygen gas. Oxygen has a double bond and 2 lone pair on each oxygen. So we're going to draw out everything. Carbon dioxide, we've drawn this lots of time. Carbon in the middle, 2 double bonds to each of the oxygen. And then we have 2 waters. So there is our reaction, Lewis structure style. Now we look at what kind of bonds I have here, and we go ahead and we look up the bond enthalpies on page 407. So if I look at this, in the methane I have 4 carbon-hydrogen single bonds. So 4 carbon-hydrogen singles. and those are 414 kilojoules per mole. I have 2 oxygen-oxygen doubles. Those are 498.7 kilojoules per mole. So that's on the reactant side, and I'm going to break all of those bonds. Now, on the other side, I'm going to make bonds, and I'm going to make 2 carbon-oxygen doubles in CO2. If you look on the chart, you'll see they're different in CO2 than they are in other things. 799 kilojoules per mole. And I'm going to make 4 hydrogen-oxygen singles, which are 460 kilojoules per mole. And I'm going to make these bonds. So when we think about bonding, it takes energy to break a bond, so that's a positive energy. When we make a bond, energy is released. And when we release, it's negative, it's exothermic. So we can add all of these up and assign them appropriately with the sign. Positive signs if we break something, negative signs if we make something. So the enthalpy change would be 4 moles of carbon-hydrogen bonds times 414 kilojoules per mole. Because I am breaking these, that goes in positive, plus 2 moles of breaking oxygen-oxygen doubles, 498.7 kilojoules per mole. That's positive energies because I'm breaking bonds. Now I'm going to subtract 2 moles at 799 kilojoules per mole because I am making bonds, so energy is released. And I'm going to subtract 4 moles at 460 kilojoules per mole. So now, all I have to do is multiply across and add these up. So the enthalpy change is 1,656 kilojoules plus 997.4 kilojoules minus 1,598 kilojoules minus 1,840 kilojoules. As we add these all up now, we follow the sig fig rules for adding, and this one stops in the tens place. Here I stop in the ones place, the tenths, and the ones, so I have to stop in the tens place, so delta H, negative 780 kilojoules. So that's a different way to find enthalpies. Not using Hess's law, not using standard enthalpies of formation, but using bond energies. Okay, there's one for you to try on the next page. Let's have you go ahead and do this on your boards, your positions on the boards with your groups.